the global computational address space, if I recall this correctly. That's one fairly modern, has lots of interesting features. And we get a bit of introduction by Dominic now about how you can use this to actually simulate actually binary systems, actually for binary systems, futures itself. But thank you.
Thanks for the introduction. So I'm Dominic Marcello. This is one of the people that have worked on Octo-Tiger over the years. A lot of people in computer science, and then there's the astrophysics group that actually does astrophysics code, and we have some people that are using it to experiment with different visualization techniques. So Octo-Tiger simulates astrophysical fluids, self-gravitating, and we use it to study binary star mergers, not neutron stars or black holes, but double white dwarfs or acyclic stars, red giants. And it uses a finite volume technique for Euler's equations, adaptive mesh refinement, fast multiple method for gravity. And then we also use it, its secondary purpose is to test HPX. So these are the equations that it's solving: mass conservation, momentum conservation, energy conservation. So with the mass conservation, we're not just evolving a single density, we evolve multiple densities so that we can track different parts of the stars that we're evolving. It's a completely passive thing. It's just it's like a tracer. So we can track where the different parts of the star wind up. You know, where each star winds up. So with momentum, we allow the frame to rotate with the original or the initial orbital period. So it reduces the velocity relative to the grid, which lowers the numerical viscosity that turns up in finite volume schemes, and it helps. It makes the evolution more accurate. We tried running it within the inertial frame, and stars wind up merging a lot quicker than they do the rotating frame. So the momentum we're actually evolving with the inertial frame momentum, but the velocities are taken in the rotating frame. As a result, you wind up with just half of Fourier's force. We have gravitational acceleration. And we've tried 3 different equations of states. So the first one here is just a polytropic equation of state. It doesn't actually have heat. We don't really use that one anymore, but when we were using it, it was used to kind of approximate the limit where the heat produced by shocks is instantly radiated away. And then we have an ideal gas equation state. And we've experimented with this analytical approximation for double white dwarfs, where it's not just the cold white dwarf equation state, but has ideal gas heating too. And we were using it for quite a while, but it turned out to have some problems later. The energy equation is a little rearranged. And we do it this way because when you take the numerical form of that, you wind up being able to conserve total energy, which is from here, of potential plus the E is kinetic and external, and potential gravity. That should be conserved. Take this form, disregards it, you wind up being able to conserve it. And this helps prevent stars from evaporating. So with the finite volume scheme, at the edge of the star, you have numerical viscosity that's going to be high just because that discontinuity there slope, and it causes mass to be unphysically moved out of the star, away from the star. But when you do that, you increase the gravitational potential, and you added energy to the system. So over time, if you have a star like that, it'll just evaporate that profile. So by being careful to evolve the total energy to machine precision, we can reduce that evaporation. And this is important because a lot of the initial conditions we start off with are close to equilibrium, where mass transfer between the stars is just starting. So it's just a little string that's actually doing something while the rest of the stars have the same equilibrium. So we use a fast multifold method, where most grid codes to use an iterative method. So with fast multifold, you have exact machine precision conservation of linear momentum. And then you don't have to worry about boundary conditions like you do with iterative Poisson solver. And we also added a feature that allows it to conserve angular momentum also without violating linear momentum. So the reason that FMN violates angular momentum is if you add up the torques from the FMN equation, you'll find there's a net torque between any two interacting cells in the hierarchy. So our fix is kind of not pretty, but we just add a constant force equal and opposite across each cell, just to cancel that out, and it's equal and opposite, so it doesn't violate linear momentum. The disadvantage is it doesn't really preserve the nature of interactions with individual particles. And also, you have to have an extra multifold moment to make the correction, which is expensive. It doesn't contribute. It doesn't make the force calculation more accurate. It's just to get that correction. But recently, Rogan out at Los Alamos was able to figure out how to do this all the right way by in a method that preserves the interparticle interactions and also doesn't require this extra moment. We don't have this implemented yet, not Octo-Tiger, but something I like to do in the future. We had tried to also conserve angular momentum hydrosulfur. The Artesian-based hydrosulfur. If you're careful about AMR boundaries. And I should say that Octo-Tiger doesn't refine in time, only in space, so that makes conservation across AMR boundaries simpler to deal with. But a finite volume method will still violate angular momentum. We played around with this method where they used basically they track the angular momentum conservation violation per cell locally, and then fed that back in the rest of the hydro equations, the way that caused it to balance out, and the actual violation minimal, summed up the corrections within the cells to 0. we can never actually do it work right, without doing things that just make sense. But there's been a lot of recent work, with that, maybe, we could use, to actually get this done. This is a goal and, early on. We wanted to be able to conserve angular momentum, for the entire code. Do it in gravity, but not hydro, you still have a violation. But it's not all a loss, because, to conserve total energy in the rotating frame of reference, turns out you have to have machine precision conservation, with the gravity. Don't need it for the hydro solver. Need it, for the gravity solver. So, it's going to do that, and that enables us to rotating frame without the stars dissipating. So our initial model routine, it's called a self-consistent field method. And it's basically an algebraic equation that gets solved. This is the enthalpy, gravitational potential. You've got a rotational potential. By setting a constants, you can determine the structure. Each star has its own constant. The method here is you kind of got to iterate and guess, and it uses 3 points, to determine, what you end up with. So if you want a Roche-Loeb filling, binary, then, you have to kind of iterate, but we've modified it to specify that it should be Roche-Loeb filling, or that it should be a contact binary, with a common atmosphere. So, let's watch the first movie. So in 2017, a graduate student, the guy who I was working with, postdoc, came out and he did some simulations. So instead of using like a polytropic model, analytical model, so use like 2 polytropic indexes, constants, to get a core envelope structure, more like a red giant star. So the cores have there's a density discontinuity factor of 2. show different features. We had extra resolution at this continuity. And it's actually on 5 orbits now, so the orbital frequency changes once things get started, and the grid is just rotating at the initial frequency. So what you're seeing is the difference between the actual frequency, grid frequency, and then we change the density scale, so you can see the orders of magnitude density that we're dealing with. So it's not pull that up. And this mass transfer is unstable, so the accretor pulls mass off the donor, sinks further into contact. I go across. So, yeah, another advantage of AMR is that grid, actually minor. So, one of the things, probably the thing we most use for, as far as astro goes, is study the formation of our borealis stars. So these are weird stars because they don't much hydrogen from helium. And I left off the other side. So the proposed formation channels were a merger of carbon oxygen white dwarfs for the final helium flash of an asymptotic giant branch star. But now the merger scenario is favored because of the ratio of oxygen isotopes. I think there'd be much less oxygen 18, but it's actually 50. And to model this, you have to get the amount of oxygen 16 that's dredged up core of the accretor as it merges. So as it merges, there's this high temperature shell that forms around the accretor where you get this oxygen 18 produced. So on this paper here, looked at, it compared results from Octo-Tiger and another code called Flower, and it also looked at SPH results. The SPH, you get enough oxygen dredged up. But with grid, because of numerical viscosity, you got too much. But with grid, you can look at convergence by making the grid higher resolution. So back to this white dwarf plus ideal gas equation state seemed to be working fine until we worked on our latest paper right here. And after a long time, relative to how long it takes the binary to merge, it winds up having effective instabilities. Stars, and we looked at it just with a single star, and it's still having instabilities. We're not sure why exactly. Ideally, Helmholtz equivalent state, which is something but for this paper, we just make sure that the binaries actually merge before this happens. So because with the grid code, you can increase resolution, you can use Richardson extrapolation on the amount of oxygen that gets pulled out of the core. This is just the way it's measured. We measured it's the amount of oxygen at densities, lower than this neutral value, 10⁵ grams per centimeter cube. So this is where the merger actually happens. These are different resolutions, and as they, they get closer to the true value, this is Richardson extrapolation, and found that getting close to the isotope ratio that's observed. Let's see if this works. We've also looked at Betelgeuse. So Betelgeuse, it's a giant star and has unusually high rotational velocity. And Manos Matsopoulos here at LSU wanted to look at the possibility that it might be due to a merger in the past. And the paper that they wrote mostly used an analytical model for the merger fed into the MESA code, which studies stellar evolution. But we also looked at it with Octo-Tiger. We kind of had to not use an ideal model because the secondary star should be almost the point mass compared to the giant. But when you add too much resolution you add too much spatial resolution without time refinement, you wind up with small time steps. So we used a star that was a secondary that was a 16th of the radius. And then we gradually added a small amount of entropy to the giant until it developed, until it started to merge with the secondary. So another thing, working with code is it's like a group that does advanced visualization. University of Stuttgart, and they're doing things like there's looking at we usually look at it just take a slice, color plot. You're limited in what you can see with that. So one of the things they're doing is like these are the surfaces of binary as it's merging, or while it's transferring matter, not during the final phase of merger, during the mass transfer phase. The surface is a iso density surface, and then it's colored by the velocity normal to the surface. So the blue areas we have matter going in to the surface. The red areas you have matter coming out. Another thing that they do is plot path lines. So you can see here, the accreting matter and where it actually winds up. It winds up this creating a tape reader. You know, so obvious. It's the color density plot. HPX is what Octo-Tiger is parallelized with. It's developed here at LSU by the Stellar Group, but there's contributors all over the world. And it's an asynchronous mini pass approach. So fine grained pass would be, you know, not like a P thread, but a user space thread. So they're more lightweight, and you have you know, thousands of them on one node without much of an overhead. This asynchronous execution, primarily through futures, and then dynamic scheduling, so that it has a scheduler that decides which tasks to execute, which order to execute the task in, and there's, you know, different queues, like one queue per core, and they can steal work from each other to balance things out. Asynchronous communication, so you can one task and receive or send a message to another task without, you know, I mean, MPI is just more that with HPX works naturally, and it's written in standard C++. So unlike other AMT is charm. You don't need anything special on it except the library, and it's C++. Usually it's standard C++, but it's standard, and it follows the similar interface to C++. So instead of standard future, you have HPX future. So this is the basic architecture. So local control objects would be things like futures, utexes, things that are local to one processor, promises, but there's also a global promise. There's the threading subsystem that selects which task to execute, which order. It's what we call an active global address space. So like a passive global address space, you can move things from one locality, one node to another, and if you migrate things, and there's futures that are dependent on those migrated objects. It's all done behind the scenes. You don't have to worry about that. And then there's the parcel transport layer, which manages communication between localities. This actually uses API under the hood. Other options with fabric. There's that's so that manages package information that back and forth between tasks. And then there's this performance counter framework. There's several built-in counters that you can use to measure things like the idle rate of each core, each system thread. And you can also write your own performance counters. Like that. So Octo-Tiger and HPX, it's also able to, use GPUs, HPX sort of has, you know, all future setup, GPU execution, CUDA or if, Octo-Tiger has SIMD also for the hydro and gravity modules, and then HPX can also use Tacos, which is a portable way to do GPU and SIMD. And these are some of the machines that we've run on the Tiger on. So done a lot of scalability studies to demonstrate how scalable HPX is, and this is the first big one. I'll explain the processors, and then all the way up here to front. There's this process. Be a little early. Questions?
So we actually have lots of questions. So yeah, I'll take this one myself. Are there any questions? Zach has a question.
Maybe it was just implied, but your penultimate slide, go back one slide. Didn't have any LSU clusters. I assume it performs fine on those as well.
Yeah.
What is the fastest LSU HPC?
I believe it's
Probably two people now.
yeah, I decided to that technically helps you. But I mean that's a long cluster, right? Yes. But Supermach 3 would be LSU. He asked if you want to use HPX with GPUs, you have to use couplers. So, those capabilities added later, but we'll first using it. Just
but slows down for short range. Start learning. That's what I'm very load code. Slow down.
question. Yeah, he asked if the FMN slowed down during the merger phase. And it turns out it doesn't. If you have, I mean, to the extent that you don't add more total grid cells during merger, like the AMR requirement, you can wind up with more total cells being tracked. But it remains ordered in. So each cell, grid cell, is treated as a point mass, like a particle. It's equivalent to a particle. So it doesn't slow down the merger except to the extent that you add more grid cells. As it merges, you tend to add grid cells as the mass starts to spread out. Track that. The hydro also slows down as well.
One of them is maybe a physics question. So when you construct the initial data, you're constructing something that's self-consistent for both hydrodynamics and satisfies the equation of gravity.
Right.
Do you only support non-rotating stars, or can these initial data stars already be rotating?
Oh, it's rotating, yeah, yeah. Well, synchronous rotation. So it's rotating, the second you probably see is the binary.
Right. And then kind of another question, a little bit similar to what Johnny asked, is so earlier in the conference, Peter quoted on the Sphinx BSSN code, which is kind of, in some sense, the opposite picture of what you have in Octo-Tiger, namely that Sphinx BSSN has SPH particles, and then a grid-based GR code underneath it. But you have a grid-based hydro code and a, well, SPH-like gravity treatment underneath, but SPH, particle-based. Can you comment on the advantages of using one or the other? Because binaries, you would get, for example, less atmosphere problems when you merge SPH code with other advantages.
I mean, I think it's more a, you can, I don't think you could do GR with like a fast multiple. So you need grid to do that. So I mean, this isn't a GR code. And yeah, we want to have machine precision. It's like comment on the difference between HPX and charm plus. Honestly, I don't know a whole lot about charm. I mean, they're similar. HPX is flying with C++ standards, so more special compiler. Designed to work on a wide range of architectures.
Right. Paul, any more questions? You go for it. Extra time. I would say we make it think that great, and we start the next talk at the same time. Last session. And this will be one remote talk. So the remote speaker is Marionette, who's practically at Federal University of São Carlos in Brazil. And he will be talking to us about advanced magic and backward jets. And if you have any questions, just interrupt. I'll try to repeat your question. Go ahead, Maurice.
Oh, okay. So thank you, guys. Well, I'm an undergraduate student here from Brazil. I'm finishing my undergraduate studies, and I'm going to talk for you about a little bit the rotating black holes and mechanism to extract rotational energy from the core of the astrophysical region, right? So, well, first of all, a little bit of me, how I found you guys, how I found Einstein Toolkit. So, I published a paper about actually your wormholes, shadows of wormholes, in 2022, and one of the authors of the paper was a visiting scholar in Rochester Institute. And well, then I searched the site of Rochester Institute, in the center of computational relativity and gravitation, and I see the tag products, and I find you guys here, the Einstein Toolkit. So just a quick comment about this paper. Well, we were studying actually the photon ring of a charged black hole. So me and Daniela, we did the analytical calculations, and then Joaquin, this third author, used a code called Skylight, and he plotted the photon ring, and he put a star beyond the mouth of the wormhole in the other patch of the manifold, right? So in the other connected region, and he put a star, a model of a simple star, and we saw a sort of Einstein ring, right? Right. So, well, about this talk. So, I'm going to talk like almost semi-technical and communication talk about black holes and the Blanford-Snarjak mechanism. So, we know about gravitation, right? So here is the Einstein field equations. And basically, these equations tells us about how matter curves the space-time, and then how space-time affects the matter, right? So here's a cartoon of the whole thing, and once again, the Einstein field equation in his whole form, right? So, okay, gravity and classical gravitation is a vast study, as we know. So we have, wormholes, warp drives, the whole cosmology, and gravitational waves, and of course black holes, right? So, and the concept of a black hole is, it's it's quite simple. Is a in classical gravity is a region of pure void, right? So it's technically the solutions in Schwarzschild and Kerr cases, solutions for the vacuum Einstein field equations, right? So we have, of course, a very important region, actually a surface called event horizon, so a null surface. So information cannot go backwards, go beyond go return, sorry, the event horizon for the universe. So basically, everything you throw in a black hole stays okay in the black hole. So the pathological feature of black holes are, of course, singularities. So general relativity in his classical form predicts, in some sense, its own failure due to physical singularities. Uh, okay, the first black hole solutions is, of course, Schwarzschild solution uh, in 1916, and its version with rotation, so a rotating black hole, is due to Roy Kerr in 1963, right? So it's a more complex metric, and you know probably we all know here that due to the cross terms in a matrix, this very feature in the metric, we can, have all sorts of new effects, like the very important one here, which is the frame dragging. So of course, the the cross terms induced this effect, the frame dragging effect, right? So, okay, a nice picture from Sage manifolds, package from Python. You can find this online very easily. So yeah, here just to depict a Schwarzschild black hole, which is the one without rotation. A here is the spin parameter, which is associated with J, the angular momentum, and the mass, right? So in a very rapid Kerr black hole, we have all sorts of new regions like the outer ergosphere and the very actually two other kinds of horizons, and another ergo surface, another ergo region, inner ergo region, and of course the ring singularity. The whole topology of singularities in this case is changed just due to rotation. So yeah, of course this mathematics here of Kerr black holes uh, is not actually accurate for astrophysical ones, because we don't expect that inner horizons or inner ergo surface exist, because there are studies about the stabilities of these inner regions, but the outer ergosphere and the very outer horizon, you know they exist, of course. Another picture here about more technically about how to define mathematically these surfaces here, right? uh, okay, so a very important feature of Kerr black holes, which is associated with what I am going to talk a little bit now, is the possibility of extraction of energy due to rotation, right? So the first person I think that uh, studied this was Penrose, right? So it's a very simple effect to understand here. So of course, the scalar here is the energy, the relativistic energy. So suppose you have particle zero here with a momentum p0, and you throw this particle in a very intelligent way, like so that in the point D inside the ergosphere, we have a decay of this particle, and some part of the particle goes in and inside a black hole, and the other one escapes from the ergosphere, right? So this effect here is very nice because we can understand, due to this effect again, the causal character of vectors inside the ergosphere. So, in fact, inside the ergosphere, observers are, observers cannot stay actually static. They must rotate in uh, at uh, the same direction, angular direction of the black hole, right? So also we have a change of causal character of vectors and physical quantities, like uh, this momentums here, these contractions inside the ergosphere. We have space-like character of vectors. So of course, the sign of the energy you know will not be the same as the sign of the energy outside of the ergosphere. So due to this causal character of this scarce space-time, just a pure mathematical thing, we can calculate the output of the energy, and we can see that the energy that goes out from from the from the black hole, due to this particle, of course, uh, is greater than the energy that entered, or the energy that the particle p0 carried. So, okay. Well, uh, knowing that about Kerr black holes and uh, the whole importance of the ergosphere. So in reality, we have, of course, not pure eternal and isolated Kerr black holes. We have a more complicated scenario which are the astrophysical black holes, which have astrophysical gas and all sorts of things orbiting the object, right? So here are two pictures of galaxies. For we can see the jets, the whole point of the talk here. So we have here a very compact and point-centered object, uh, throwing out matter from its center. And the very famous one, Messier 87, we also have this structure, this jet, which is called. So again, we have a jet coming out from the center of the whole galaxy, and uh, the center of the object must be a very powerful thing, because this is a whole elliptical galaxy, and we have a structure that is reaching out its boundaries in some way. So it's a matter that coming out very uh, a very center object, and is traveling through thousands of light years from the center, right? So which mechanism can do that? Again, another picture, a composition of Centaurus, I think. So we have whole galaxies and huge objects expelling matter. So of course the standard model here of active galactic nuclei are the black holes powering these jets. So okay, a little bit about the mechanism. So as I said, astrophysical black holes are not isolated. So we have the astrophysical gas and all other sorts of matter uh, orbiting the compact object. So in a form of accretion, right? Accretion, forming an accretion disk. But as we know, most of the astrophysical gas carry a component of magnetic field, so they are magnetized, like the sun expelling coronal ejectors. These are carrying field lines of the magnetic field, and these clouds interacts here with the magnetic field of Earth and so on. So in the interesting case of black holes, we also have these magnetic field lines, but due to relativistic behavior and extreme gravity around these objects, we have uh, uh, in this accretion disk we have a convection of the poloidal magnetic fields, right, due to the accretion. And yeah, here we can see a cartoon of what is happening with the magnetic field lines carried by accretion, right? So it's very interesting because we have this poloidal magnetic field lines components here coming from the outer accretion disk regions. And as soon as these field lines reach the magnetosphere, which is more or less bounded by the ergosphere, uh, these field lines are, of course, they 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 are they experience a torsion of the they experience a torsion, right, due to the rotation, extreme rotation of the object. So this rotation creates another sort of configuration of the magnetic field, which are the the toroidal magnetic field lines. So, and yeah, It's very interesting because in this other cartoon here, we have again the depiction of the magnetic field lines coming in the encountering the black hole. And then, as I said, we have, due to the rotation of the black hole inducing a twisting of the magnetic field lines, we have an appearance of toroidal magnetic field lines. Also, of course, we have poloidal electric fields, induced electric fields. So, yeah, the Poynting flux, and this is the main information here. Here, of course, we have the poloidal electric field and toroidal components. As we can see, I put this just to comment that the electric field, the toroidal electric field, is zero here in this region. So, in a very simple way, we can calculate the Poynting flux between the poloidal electric field and toroidal magnetic field, and we can see that we have a flux coming out from the black hole, right? Due to this magnetic and electric field configuration. Of course, this is a excerpt of Blanford paper. So we, as external observers, we see a strong flux, right, so of energy coming out due to this mechanism that I comment here now, right? So I'm gonna pass this a little bit, and the very form as first calculated in the paper, which is the theoretical prediction of the effect, which is the the pointing the the value of the Poynting flux here. Well, we have, of course, the vector field here, the vector potential, right? So, and we have here the rotation of the event horizon and the rotation omega, the little omega of the magnetic field lines, the toroidal, the twist. This quantity says to you that very close to the black hole, the poloidal magnetic field have angular component here, angular velocity component, right? So another important quantity about this effect is the power that we can calculate, right? So here we can uh, calculate using the energy momentum tensor, but the first version of this calculation, due to Blanford and Snajic, I think that is in the first paper, uh, is the power that we can associate it with this effect, which is the very famous
5
Blanford.
minutes, please conclude.
Okay, sorry. Which is the very famous Blanford-Snajic power from the system, the output power. So we can see here that you know is defined using the magnetic flux and the very angular velocity of the black hole, right? So another interesting fact of BZ mechanism is that is believed to be independent of the scale. So we have quasars and microquasars, but both of them exhibit the jets, right? So But of course, the scale between the two are very, very different. One is a galaxy, and the other one, is the is a stellar mass black hole, not a supermassive one. So yeah, here is my references, and yeah, thank you for your attention and the opportunity to talk here.
Quick presentation. You actually have quite a bit of time. The 5 minutes, one was 5 minutes to your question. So if you have something more that you'd like to present, you can use up that time. What about you? There you go. Can you hear me?
Yes, of course.
I was saying you actually have a little bit more time. The 5 minutes only was 5 minutes before to your question. So you have about 7 minutes or so left.
Oh, do we have questions? I am not hearing well.
Let's see. Are there any questions in the room, actually? Any questions online? I have some question. Mostly just, I think it was very nice to see the description of how the magic works and the Penrose process as well. Now, ever having worked on this myself, I'm wondering if you have a way to make it intuitive why exactly the magnetic field lines actually twist
2
out
minutes.
from the black hole. Is it just a frame dragging effect, or is there something else that I can think of that needs to be particles that get dragged along as well?
Well, I'm sorry, I didn't hear well the question, but I think that you said about the main effect that twists the magnetic field lines. Am I right?
Yes. Yes.
Yeah, as far as I understood the effect, so of course we have the accretion disk, so the whole disk is spinning, but and of course uh, together with this accretion spinning induced by the spinning of the black hole, we have the matter falling in the black hole. So due to the magneto hydrodynamic physics of the accretion disk, we have this that colloidal components going going in together with the matter. But as I said, as far as I understood the fact, you know, uh, close to the close to the black hole, and of course close to the ergosphere, we have this effect, which is due to the frame dragging. Uh, this effect that is, of course, the frame dragging. The effect of rotation, and as I said, the frame dragging per se twists the magnetic field lines.
Okay. Thank you. Let me see. Oh, there's one question locally, Johnny.
One question about the utilization that related to your previous paper. And so about using, of course, the skylight, I'm wondering how experience, how you need any memory get work on it.
Okay, let me repeat the question because it didn't quite go through. But it's a question.
Okay.
And it's now about the visualization slide that you had and the skylight package, and basically how much memory and how much compute power one needs to do these sorts of visualization.
Well, these exact numbers I don't have because it was all Joaquin's part of the work, but it was not very uh, cons- uh, you know he didn't use much computer power. Of course, as far as I remember, he said to me that one simulation was about 2 or 3 hours, I think. But it's not a question of days or weeks, to simulate these Einstein rings here. So it's comparatively from the other lectures here about adaptive mesh refinement and the other sorts of things. I think he did this in his laptop, I think.
Okay, thank you. Let me see. Any more questions? Call for questions online or offline? Okay, you are kind of competing with lunch, but thank you very much for a very interesting talk.
Thank you, guys. I'm gonna stop sharing now.
So yeah, lunch for the next hour. Afterwards, we're back in this room.